Hello, my name is Patrick McCardle. I'm a mechanical engineer with the Institutional Consultation Services, or ICS. We're part of the Francis J. Curry National Tuberculosis Center. Our services include on-site consultations to staff in institutions at a high risk for TB. During our visits to hospitals and clinics, we have found a general gap in knowledge regarding engineering controls. Often, staff assume that everything is working correctly, but don't know how to confirm this, or else they suspect that it is not, but don't know how to check it or get it fixed. There's a need to educate staff on how to do simple checks of their ventilation systems. The first step is for someone to determine whether or not there is a problem. This video will show you how to assess some engineering controls in healthcare facilities. You'll also see the instruments that engineers use and how they are used. Obviously, we don't have time to cover all aspects of engineering controls. We'll concentrate on some ventilation concepts that are important to people in many different disciplines. In particular, infection control coordinators, safety officers, employee health practitioners, and facility engineers. Since negative pressure isolation rooms are designed specifically to control infection, we'll use an isolation room to illustrate some of the basic concepts of engineering control. These concepts include ventilation, exhaust, negative pressure, and room clearance time. Later, we'll talk about two other high-risk areas in the healthcare setting, sputum induction areas and waiting rooms. I'd like to introduce you to my colleague David Sasai, another mechanical engineer with the ICS. David's the quiet one. David will be demonstrating the various checks and equipment that you can use. David and I hope to introduce you to engineering control concepts in as straightforward and painless a way as possible. In isolation rooms, ventilation helps to control infection by diluting and removing infectious particles and by controlling the direction in which air moves. The Centers for Disease Control and Prevention, the CDC, has published recommended standards for new or renovated isolation rooms. The minimum recommendations include a ventilation rate of at least 12 air changes per hour. The room must be under negative pressure, and air from the room must be exhausted to the atmosphere or HEPA filtered. We'll discuss what each of these recommendations means and show you how to verify if your isolation room meets the standards. Let's start with ventilation. Ventilation is the most important engineering control. The first thing we would like to know is how much air is moving through the room. The ventilation rate is the amount of air that leaves, is exhausted, or enters, is supplied over a specific time period. Most spaces should have a return or exhaust outlet, usually called an exhaust grill, and a supply outlet, usually called a diffuser. The exhaust can remove infectious particles. The supply air dilutes infectious particles. You can remember this by the phrase, the solution to pollution is dilution. The outlets are usually at the ceiling, but can be on the wall. An easy way to see if an outlet is supply or exhaust is to hold a tissue against it. An exhaust or return will try and suck in the tissue. A supply will try and blow the tissue away. The most common way to quantify ventilation is an air changes per hour, ACH, which compares the airflow to the dimensions of the room. The ACH is determined by a relatively simple calculation. The amount of air that is exhausted from the room each hour divided by the volume of the room. The exhaust air rather than supply is used because it is the exhaust that removes any airborne contaminants. To find out the number of ACH provided by a ventilation system, you'll need two pieces of equipment: a flow hood to measure the airflow and a tape measure to measure the room dimensions. The first step is to calculate the room volume in cubic feet. The tape measure is used to measure room dimensions. These dimensions are used to calculate the room volume. The volume is the length times the width times the ceiling height. We'll illustrate this with a simple example. Assume a square-shaped room 12 feet long and 12 feet wide with a 10-foot high ceiling. This would give you a room volume of 12 by 12 by 10 or 1440 cubic feet. Step 2. calculate the amount of air exhausted every hour. Measure the exhaust air using the flow hood. Flow hoods usually display the airflow directly in cubic feet per minute, or CFM. Multiply the cubic feet per minute by 60 minutes to determine the cubic feet of air per hour. Going back to our example, if the flow hood reads 180 CFM, multiply this by 60 and you get 10,800 cubic feet of exhaust air every hour. Step 3. Calculate the air changes per hour. Now you know the amount of air exhausted every hour and also the volume of your room. You're ready to calculate the air change rate. Simply divide the exhaust by the room volume. For our example, this means dividing 10,800 cubic feet per hour by 1440 cubic feet. The result is a ventilation rate of 7.5 ACH, which you'll notice is less than the recommended 12 ACH. If the ventilation is inadequate, it should be increased to at least 12 ACH. In this case, what you have to do next is calculate the total CFM required to provide the 12 ACH, and then by comparing this to the CFM you measured, you'll know how much more air you need. We'll call this step 4. Calculate additional CFM required to provide 12 ACH for the room. First, you multiply the room volume by 12 to get the volume of air in cubic feet required every hour. Divide this by 60 minutes to calculate the total CFM required. Subtract the measured airflow. In our example, this means we multiply 1440 cubic feet by 12, divide by 60 to get a required CFM of approximately 290 CFM. We measured 180 CFM, so we require at least 110 additional CFM. So, where can you get this extra air from? Well, you have two basic options. You can either increase airflow by adjusting, also called rebalancing, the mechanical system to exhaust more air. This means adjusting the ventilation system that serves the isolation room and should only be done by facility engineers or by a certified air balance contractor. Or you can use a HEPA filter unit to make up the required CFM difference. Next, we'll talk about what happens to the air after it leaves the isolation room. Air from isolation rooms or other high-risk areas should not be returned to a ventilation system where it could be recirculated to other rooms. You should find out what happens to the air after it is exhausted from your isolation room. Your facility engineer should be able to tell you. It should be exhausted directly outdoors, at least 25 feet away from outdoor air intakes, doors, operable windows, or occupied areas. If a suitable exhaust location can't be found, the other option is to disinfect the air by passing it through a HEPA filter. Which brings us to our next topic, HEPA filter units. These are examples of high-efficiency particulate air filters, also called HEPA or HEPA filters. Filters such as these remove all particles in the size range of airborne TB droplets from the air that passes through them. HEPA filters are used in self-contained HEPA filter units, which consist primarily of a HEPA filter, a fan, and a pre-filter. They provide very clean HEPA filtered air that can be used to supplement a building's ventilation system. Therefore, they can increase the effective air change rate in a room. These units come in a number of different configurations. The most common are small portable units that can produce 100 to 400 CFM. The larger portable units are rated for 150 to 800 CFM. Other designs include ceiling-mounted and wall-mounted units. The actual amount of air produced by these units is difficult to measure compared to a ceiling or wall outlet, because you can't just put a flow hood up against them. Also, they may produce less air than the nameplate lists. We recommend that you size them to produce about 25% more capacity than you want. Also, these units can be noisy, especially at the high fan setting. We recommend that you select them based on the airflow at low or medium speed. Locate the units at an elevation which allows air to be discharged from the unit to the staff at approximately head or breathing level. The discharge can be determined by moving your hand around the unit until you feel the air. When properly located, the staff should feel gentle air movement. HEPA filter units require very little maintenance. You should check the manual that comes with the unit, but in general, the pre-filters should be changed every 6 months, and the final HEPA filters should be changed every 1 or 2 years. Make sure that you change the filters and dispose of them in accordance with local requirements. In some areas, you may be required to wear respirators when changing the filters, and also to treat the discarded filters as medical waste. That's it for isolation room ventilation. Let's move on to negative pressure. Negative pressure means that when the room door is closed, air is flowing into the room from under the door. No air from the room can escape out to the hallway. Whether or not a room is operating under negative pressure can be verified by a number of cheap and easy techniques. What you need to confirm is that there is an air current flowing into the room from under the door. The most common method is smoke testing. You can buy smoke tubes such as these from safety supply companies. Slowly release the smoke in the hallway at a point about 2 inches out from the center of the door. Aim the smoke in a direction parallel to the room door. If the room is at negative pressure, the smoke will be seen to go under the door and into the room. The test should be repeated at least once or until the results are consistent. If smoke tubes are unavailable, you can use incense sticks to generate a stream of smoke. In this case, we recommend that you use at least 2 sticks. Lastly, you can also confirm negative pressure using a telltale device, which can be something as simple and readily available as a piece of facial tissue. Tear off a small strip of the tissue and hold it at the gap under the door. If the room is under negative pressure, the current will try and pull the tissue into the room. The intent of negative pressure is obviously to keep any infectious particles generated in the room from escaping to the hallway or another room. It's achieved by setting the mechanical system so that more air is removed or exhausted than is supplied. The difference or offset causes air to be continuously drawn into the room under the door. The faster the air moves under the door, the better. Negative pressure will be compromised by any leaks in the room, such as holes in the ceiling tile, or openings around light fixtures, or open or leaky windows. Negative pressure should be verified and documented every day while the room is occupied by a known or suspect TB patient. Otherwise, it should be verified and documented at least once a month. Records of this testing should be kept. Once negative pressure has been verified, the next step is to measure the strength of the pressure difference. There are 3 ways to measure the pressurization of a room. You can measure the pressure difference directly with a room pressure monitor or a micromanometer. This will tell you how much the pressure is in the room compared to the corridor or anteroom. Or a velometer can be used. This is an instrument that measures the speed of the air going in under the door. And finally, there's the amount by which exhaust exceeds supply. This is called the offset and is expressed either directly in excess CFM or else as a percentage. For example, you could say that a room is 10% negative. This means that the exhaust air quantity is 110% of the supply. There's more detailed information on negative pressure in the CDC guidelines, including recommended minimum values. However, higher pressure differentials can more reliably ensure that negative pressure does not fluctuate and remains effective. We recommend the facilities try to achieve a pressure differential of at least minus 0.03 inches water gauge. To increase negative pressure, you have 2 options that you can discuss with your engineering department. The mechanical system can be rebalanced to exhaust more air, or a large HEPA filter unit can be placed in the room with a portion of the discharged air routed through the window to the outdoors. The most common way to measure room pressure is using a permanent room pressure monitor. That's our next topic. A room pressure monitor is an electronic device that continually measures the pressure across a room boundary. It consists mainly of a sensor installed through the wall and a panel that displays the sensor pressure reading, usually in units of inches of water gauge. The measured pressure is compared to a reference pressure value. The monitor is usually programmed to sound an alarm when the pressure falls below the reference pressure and stays there for a certain length of time. The reason for the time delay is to allow staff time to go in and out of the room without the alarm sounding every time. If you have a permanent room monitor installed, you don't need to check negative pressure daily with the telltale, but someone should read and record the monitor pressure reading daily when the room is in use for a TB patient. Also, you should verify negative pressure with a telltale and test the monitor monthly. You can test the monitor by holding the door open for longer than the time delay and ensuring that 1, the alarm sounds, and 2, the pressure reading goes close to 0. The monitor may be connected to a central system that will alarm at a remote location, such as the central plant or the central switchboard. Before you perform the test, make sure you coordinate with your engineering department. It's very important that all the tests we've shown are performed, explained, or witnessed by the staff that depend on the controls, so that they can fully understand how the controls work and how they can be verified. Another area where staff communication is crucial is the issue of room clearance time. When an infectious TB patient walks out of an isolation room or a sputum booth, he or she may leave some airborne infectious particles behind. Before another patient or a staff member enters the room without wearing a respirator, you must allow sufficient clearance time for the ventilation system to remove most of these particles. The percentage of particles removed is called the removal efficiency. The CDC recommends that you allow enough time to remove at least 99% of airborne particles. For a given removal efficiency, the clearance time required depends on the air change rate and also how well supply air mixes with room air. The CDC guidelines include a table on page 72 to help estimate the required clearance time based on the air change rate of your room or booth. However, if you read the small print, you'll notice that the times given in the table are for the ideal case of perfect air mixing. The mixing factor is very difficult to calculate exactly. We generally assume a mixing factor of 3 for a room in which air movement seems comfortable and which has a ventilation rate of at least 12 ACH. A higher mixing factor should be used for rooms that are stuffy and have lower ventilation rates. Let's do an example. For a room with a ventilation rate of 12 ACH, the table indicates 23 minutes for a removal efficiency of 99%. Multiply this by an assumed mixing factor of 3 for a required clearance time of 69 minutes. Finally, it is important to make sure that all employees know when the room is safe to enter. This can be done by placing a sign on the door indicating when the clearance time is over. Our last 2 sections will cover sputum induction and waiting rooms. As I'm sure you know, sputum induction is a high-risk procedure. It should only be performed when using specific policies and procedures and in a designated area with specific engineering controls. If sputum induction is done in your hospital or clinic, you should check the engineering controls that are in place. The safest option is to use a source control device, such as a sputum induction booth or tent, which completely encloses the patient, or a partial sputum induction hood, such as this. The advantage of these devices is that they capture infectious particles so that they are not released into general room air. You should also check using a velometer that the air velocity is at least 200 feet per minute at the side of the patient's head. The hood should be placed away from other air currents, such as those created by open doors or windows. This can be verified by smoke testing. Most booths and hoods use a pre-filter and a HEPA filter to disinfect the air before returning it to the room. Others directly exhaust to the outdoors. Exhaust from booths should be treated exactly like isolation room exhaust air. Either discharged at least 25 feet away from openings into a building, or else HEPA filtered. If a booth is unavailable, a designated room should be used for sputum induction. Engineering controls should meet all the minimum requirements that we outlined for isolation rooms. That is, at least 12 ACH, negative pressure, and direct or HEPA-filtered exhaust. And, just like with an isolation room, you'll need to estimate and enforce a clearance time between patients. We also recommend that you verify negative pressure before starting that day's sputum inductions. Paying attention to isolation room ventilation can help you reduce the risk of TB infection from known or suspect infectious patients. To reduce the risk of infection from an unidentified patient, you need to look at other areas of the hospital or clinic that may be at risk, such as waiting rooms. Waiting rooms are often high-risk areas, especially those in emergency departments and public health clinics. We recommend that ventilation systems for waiting rooms and other high-risk congregate areas include the following characteristics: a minimum ventilation rate of 10 ACH, direct exhaust to the outdoors or HEPA filtration, and directional airflow from staff areas to waiting areas, especially where waiting areas are adjacent to reception desks. You should also check that occupied rooms adjacent to the waiting room are not under negative pressure. Well, that's our presentation. We'll end with a short summary. I hope that you learned some useful tricks of the trade and now feel encouraged to try out some of your new expertise. Regular assessment of engineering controls will reduce TB transmission, ensure compliance with standards, provide peace of mind, and reduce your risk of liability. Some things you should now feel comfortable doing include assessing engineering controls for isolation rooms, sputum induction, and waiting rooms, calculating air change rates, using and placing HEPA filter units. You should know how and when to verify negative air pressure. You should know how to use and check room pressure monitors, and how to estimate room clearance times. We've also shown you some equipment, such as a flow hood, HEPA filters, and various meters. However, in doing so, we are not endorsing any particular manufacturers. Engineering controls can reduce the risk of TB infection in your facility, only if they are operating correctly. Ventilation systems do drift out of balance, and equipment does break down. Regular checks will help your facility identify and correct problems quickly. Remember, don't just assume that someone else is checking engineering controls. Either do it yourself or make sure that it is being done by someone else. Thank you very much for your attention.